just make a comment and then we'll move on with the rest of the proceedings today. So, really interesting article, about a technical solution, to a problem. And what fascinated me, and it actually connects to the class today, because I'm going to talk about phytoplankton and the connection between living processes and global climate change. And there's a lot of interesting interactions among some organisms, some which are beneficial to both. That's called symbiosis. So that as an example of the complexity of restoring a system is not just bringing back kind of the players that were in that system before, but understanding how they interacted with each other and bring them back in a way in which those interactions can continue. Right? That was an interesting paper there. Okay, so let me tell you first a quick announcement about the week. You probably saw I usually post a overview of the week online, so you probably saw it, but I'll highlight a couple things that are different from other weeks. So today we have our lectures, both Esther and I, and then tomorrow's seminar. Seminar is back to a regular location in it's the third floor E, and we'll finish the book on Under White Sky. And I added a couple articles on geoengineering, so that I think that'll contribute to the discussion from that book. And I made it optional for you guys to see a fun movie on the Kanto. So I hope you get to see it. It's kind of really interesting. It used to be a kind of cult film back then, and then the link I gave is for a shortened version. You can see a longer version if you're curious as well. Thursday, we're going to be in the lab. The room is 1050. In some older silos might say 1040. Doesn't matter. They're adjacent to each other. And you'll learn how to use compound microscopes, and we'll look at phytoplankton. You'll learn how to identify major forms that are hopefully present here in the winter, and learn how to size them. And in the afternoon, there'll be a short session, 1 to 2:30 in the basement of Lab 1. We have amazing facilities at Evergreen for doing science. We have an advanced microscopy suite with scanning electron microscopes, other scopes that everybody can access to, even if you're not a scientist, if you get certified to use them. So it's a fantastic resource. So we thought it'd be beneficial for this introductory class, those of you interested in science, even if you're not interested in science, can have application of the microscopy. It'll be a little tour or a demonstration of all those different scopes. So I think you'll enjoy it, and you'll help benefit your choices as you get informed about what to do as you proceed in your academic career. Okay, so that's what's coming up. Friday, there's no class. It's part of our adjustment to make 14 credit, but there's assignments due, and also next week we have the midterms. So the midterms essentially is a lengthened version of the quizzes. They'll include some essays, and now there will be, during the time that I have lecture, instead of doing the lecture, you'll be in a comfortable location somewhere, and then you'll do it online. Okay, so the same time as you would be in lecture, but this time you do the midterms. Okay, great. So that's kind of the big overview of this week. So the first thing I'll do is quickly go over the quiz. Get a quiz is a good way to kind of go over items that were important and to highlight things that maybe were confusing for you to ask questions if something was not clear. And once we clarify everything, some of these things may appear on the midterm. So statistics. So what I usually do, people did pretty well overall. 24 minutes, so it'll give you an hour. So similarly, we give you, for the midterm, we'll give you, I think we planned it for an hour. But we'll give you, in my case, I'll give you 3 hours. And we can start at 9, so it'll be 9 to noon. Actually, I'll send an announcement for that. I usually mean for class 10 to noon. You can start it early if you wish. Okay, so let's look at how people did. First one, no problem, 91% correctly. The types of heat, nobody had a problem with that one. Next one, how the atmosphere interacts with the ocean to generate different types of circulation. Again, no problem there. Oh, this one, only 64% answered correctly. Okay, so the question was, over 50% of fish caught commercially are harvested from the open ocean. which encompasses 95% of the world's ocean surface. It's not correct. What I tried to highlight, and after I go through the slides, I'll show you there was a slide that showed that. Maybe not too clearly because I know a lot of people missed it. But the purpose of the slide was to show the importance of the coastal zone, and I had a pie chart. And the pie chart showed the percentage of commercial fish that were caught in different locations. And the striking thing was like 21% was caught in the upwelling zone, which is only 0.1% of the world's surface area. And the open ocean, even though it's a huge expanse, it's, most of the ocean is considered the open ocean, deep, far from the coast. I think it was only, I'll show the pie, but it was only like 5%. So it's really striking. And I want to emphasize that because when I studied oceanography, way back when, the public conception is that the future of the world's food production was the oceans. We could rely on these immense, vast oceans to feed the world. And it's not quite correct because most of the biological activity is close to the coasts. And again, most of the fish caught commercial close to the coast. Okay, so that's one of the things I want to highlight. And I'll show the pie chart later on, but obviously something I could have stressed more, which I'm doing now. Okay. Great about upwelling. People are recognizing what happens to the Curls effect. Things are deflected to the left of the motion in the southern hemisphere, north of the motion in the northern hemisphere. So people correctly figure out where the direction of the water would be given the direction of the wind. Here, the El Nino and La Nina, I have to check it. Canvas is really picky about spelling. So you can tell me, if some of you misspelled or something, let me know. So that could have been the reason. But what I was looking for is definitely La Nina and El Nino represent two extremes of this kind of pendulum of climate change. It's a natural oscillation of climate. It has an interannual periodicity. We're still trying to figure out exactly what is interannual the periodicity by which they occur. But now we understand the phenomena fully. Before we thought El Nino was an isolated phenomenon, but it's part of this cycle that the world climate experiences, again, over a multi-year cycle. And the two extremes of the cycle are La Nina, where if you look at the behavior in the equatorial Pacific, the upwelling is stronger than normal. So the water in the equatorial Pacific is cooler than normal. During El Nino, you get a reversal of the winds or the pressure systems that dominate the weather or the climate in the equatorial Pacific. The winds weaken, and you essentially get that warm water is typically pushed to the eastern part of the Pacific. The western part of the Pacific, western part sloshing back to the east, warming the equatorial Pacific. So A1 was La Nina, right? The water are colder than normal, and El Nino is warmer than normal. Okay. From my experience teaching quantitation, we're not doing a lot of quantitation this quarter, but it takes practice, right? So I found this a good exercise to get people to practice. And the percents are increasing, so I'll keep asking if there's 100%. Everybody gets it right, okay? So here we go. Salinity varies widely with location. So I gave you the analogy of the cheesecake, right? The cheesecakes can vary in amount, depending on the bakery you go to, but the recipe stays the same, right? So let's look at this one. So salinity, we go S, and we say magnesium is always 4% of total salinity. So magnesium times 4%, which is 4 by 100, equals the magnesium. So I told you what the magnesium was. Magnesium is 12. 12, right? So basically, we're just dividing for this 0.4. 0.4, that's 4%, right? So we just solve by dividing by 0.4. Let me see the 4, right? So you can do it in your calculator, or it's basically 12 divided by 4 is 3. There's a decimal, but it's 30. So 30 parts per 1,000. So that was the answer. A little bit of math. There'll be a little bit more math when we do the microscopy. There's some ratios there that will help you jog your knowledge of ratios. I have Thursday we'll do that. Okay, so next one, estuaries. Great, because that's the one, and I think I did stress it last time when we talked about how sediments get deposited in the estuary. There's two ways in which sediments from the river gets deposited. One is the lowering of energy as the river hits the estuary, which is broad and is protected from the wind. There's little mixing, so the sediments settle. And the second one is that process of flocculation, where salt water has different charges, particles that come from the river are small, acquire charges, they settle, right? So two important processes. And I think it says 45% because I think maybe not everybody answered them both, so, but at least people recognize each of them as being important. So, take home message, there's two processes, okay? This one, 36%, why would that? Maybe because there were two, everybody chose this one, photosynthesis high near the surface, but not everybody chose the second one, okay? So, yeah, oxygen, obviously it's a super important gas, is produced biologically, right? Molecular oxygen is it's hard to make oxygen without photosynthesis, right? So most of the oxygen you see in the atmosphere is a product of photosynthesis, pretty remarkable. I think 21% of the atmosphere is oxygen. So think about it, and that connects to today's discussion. Life is not only affected by the environment, but has a huge influence on the environment itself. So presence of oxygen is an example of that. So a lot of the production of oxygen in the water is due to photosynthesis. So it allows us to use those concentrations to track where biological activity is. We have to remember, however, that there's a physical chemical process by which oxygen from the air enters the water, basically diffusion. And those two things put together explain why there's more oxygen on the surface in the profiles in the water column, right? So there's sunlight, you're close to this big reservoir of oxygen, any mixing gets oxygen to the water. So those two reasons account for the profile that you saw with decreasing oxygen with them. Right? More photosynthesis because of more light on the surface, and there's more oxygen close to the surface. The only thing that could be different, I mean, I'll mention it now because the people that took this class in the fall, when they went out in the field, they did see a subsurface peak of oxygen. So why would there be something below the surface? Any ideas? Why would you find that? This is what we found in the butt inlet. This is oxygen. This is all oxygen here. Okay? And this is depth. And this is the surface. And this is the up to the bottom. Right? So what we saw in almost all stations was oxygen was high and pretty much went down. And in the fall, and I've seen this in the spring, it'll be high here. So this is winter, spring. So what's happening here? What could explain that there's more oxygen a bit closer? Yeah, that's great. That's great. There seems to be more algae here. So why would they be sitting here in the bottom? Not in the bottom, in the middle. What's in the middle? You guys, you saw that when you plotted. The stratification, right? So you guys remember when we did the stratification lab where the ping pong ball is at? Mm-hmm. Right? So when you have stratification, you have a lot of phytoplankton. There's two things that are happening. On the one hand, they're eventually sinking. A lot of the plankton that you see can't swim against the current. So they'll sink and then they'll accumulate at the picnic line. Right? There's another thing in the summer. There's another organism, and again this relates to it. I talk about phytoplankton, maybe I'm getting a little ahead, but it's related. There's an organism called a dinoflagellate, and the dinoflagellates are pretty clever. Anthropomorphize it, right? But because dinoflagellates can swim, so what they do is they swim to the surface during the day to get light, and at night they swim to the picnic line to get nutrients. So they get to both worlds, right? They can go back and forth. Okay, great. There's a third reason that we're gonna peak of the summer. Actually, if there's too much sun, ultraviolet light can be an issue. So some organisms either inhibited by the too much light, or their optimal photosynthesis a bunch of interesting reasons for that. Okay. But for the purpose of the quiz, just to understand what controls oxygen, this is the two things I was looking for. Okay, this one. Okay, yeah. So it's a good one to highlight. This one a lot of people missed. Okay. So in San Diego beaches, we went to the Evergreen Beach on Thursday. People experienced anoxia, right? It was anoxic, and I kind of explained it. So I changed my explanation here to make it false. So I think people just talked about the oxygen. Okay, so let me go through over this. Okay, so the reason you get that black layer that's anoxic is because there is high organic matter. I put there low organic matter. It's a lot of organic matter. So one thing that you should have cued into is that the decomposition is because the huge amount of organic matter leads to a lot of decomposition by bacteria. So I'm going to talk about bacteria today. We're making all these connections. And heterotrophic bacteria, not photosynthetic, so they're breaking down organic matter. They're using oxygen in the process, and they draw the oxygen down. So just right below the surface loss on this oxygen. Okay? And it's bacteria, not algae. Right? So algae is photosynthetic, so algae produce oxygen. So it's not related to the anoxic condition. So there's two things that should have cued you. It should be high organic matter and not algae, but bacteria. Bacteria consuming large organic matter is what algae else. Okay? And everybody, oh great, okay. So this is how you lose heat. I asked you that because we want to make sure people know about that process. Actually, it's important to educate you about how to protect yourself when you're in the environment. Right? Spend a lot of time outside. You need to know how you lose heat and how to prevent those losses. Okay, great, excellent. Okay, so I'll start my lecture. This is just that. I'll show you the. Like this good. Let me just kind of this. There. I think that's good. Okay, so this illustrates the importance of the coastal zone. We'll actually go back to it a little bit today. But so here's the coast of Peru and Ecuador. A big upwelling area. This shows how upwelling occurs, nutrient-rich porous coastal surface, huge amounts of productivity. During the peak of the Peruvian fishery, and I think it was in the 70s, 20% of the world's catch was in the coast of Peru. And then El Nino kind of made it, a bunch of subsequent El Nino plus overfishing made that collapse. It's another story, but a hugely important area, it still is. But this is that pie chart I was talking about. The open ocean here is 3.8% of the surface area of the ocean, and sorry. This is the percentage of fish that are caught, right? So in the open ocean, only about 4% of the fish are caught in the open ocean, which is like 90% of the world's surface area, world's ocean surface area. So most of it's a coastal zone. This highlights the importance of upwelling regions and also coral reefs, things that we're concerned about protecting. This is an explanation why they're disproportionately important in sustaining things that humans care about. Fish. Okay, so let's talk about today. So we're transitioning now into understanding climate and the influence of carbon. Right? And it's crucial because carbon is a thing that humans can influence. Right? So we're connecting climate regulation processes with non-human activities. And we'll talk a little about phytoplankton, and hopefully you can see the connection right here. The carbon cycle is driven by not totally, but it's a huge source of the driving of the carbon cycle is living things, microscopic things in the ocean, phytoplankton. And we'll have a chance to supplement this lecture with actually looking at phytoplankton on Thursday. Okay, so we're going back to this. We're trying to develop the science underlying this climate system. Right? So again, the climate is complex. Maybe I'll add a couple things here. So some of the text that I've been showing you, sometimes I don't talk about it too much, but now's the time to start adding the complexity of it. Okay? So first, to remind you, the solar energy basically drives the system. So you might think ahead. We have global warming now. So a possible explanation is that there's more solar energy coming in. Right? So that'd be an obvious thing to test, right? So is the sun getting hotter, or fluctuations in solar energy explain the changes? That, as a scientist, that's one of the very first things you would explore, because that's a major driver of climate. And all those little arrows indicate the movement of solar energy heat throughout the different compartments, and eventually it's balanced by how much is reflected out to space. So we have this steady state of what determines a current climate, but it's certainly changing. What's causing that change? Well, we're going to look at the interactions of these different compartments. We already looked at the atmosphere and the hydrosphere. Those are the first two chapters, right? We talked about the oceans, the atmosphere. We looked at the interactions. And now we're going to start talking about the biota. So the biota is connected to all these things, including the solid Earth, by the carbon cycle. Okay? So that's why we need to learn a lot about it. Let's talk about some of the terminology that's here. Okay, so some technical terms for solid Earth, ice, water, and air, and living things. Litho, rocks, cryo, ice, hydro, water, atmo, air, bio, living. Spheres is, encompasses each of those. Okay. It's complicated because there's many components and they're dynamic and nonlinear. Things are changing all the time, and when one changes, the other compartment doesn't react. It doesn't react linearly, meaning that if you have a 10% push in one direction, it doesn't result in 10% push in the other compartment. So there's some complications in their interactions between these compartments. New term, maybe not new to you, but maybe you should recover this class. There's things we call positive and negative feedback loops. So when there's one change in one compartment affecting another one, there's two ways in which the change can occur. It can be positive meaning that the change is amplified by this other compartment. And it can be negative, where the other compartment actually resists the change. So positive is amplified, negative resists. Okay? Give you some examples. A positive feedback loop is an example of it. The Earth is getting warmer. That leads to the ice melting in the ice caps. Okay? As the ice caps melt, the area that's white, that's reflected, gets reduced. So the smaller the ice cap, the less reflection, and the more the Earth warms. So that change of heating the ice caps gets amplified by the melting of the ice caps. So that's a positive feedback loop. So a little change leads to a bigger change that keeps amplifying itself as it progresses. Negative feedback loop is one that resists. So a way to indicate that is the formation of clouds. The warmer the climate, the more cloud formation. And if these clouds are at high altitude, they actually become more of a reflective surface. So it's kind of like the ice, right? So you have more heat, more water vapor, more clouds. If the clouds are high, they reflect to the atmosphere the solar radiation, and they start to cool the atmosphere. So that would be an example of negative feedback. Does that make sense? Clouds are a little bit tricky because actually we're experiencing it in this weather these last few days. If the clouds are lower altitude, they actually have a warming effect. They're like a little blanket. So it was warm when it was cloudy and rainy, and rain when it rains, you get release of the heat as the water goes from the gas to liquid. And the last few days have been clear, so it's been really cold because we don't have a little warming, and there's no rain releasing energy. Okay, there you go. So some new, hopefully new terminology to guide you through some more technical literature. Okay, so we're going to do the carbon cycle. So what things to cover today. So here we go. This is a big picture. I'm going to talk about the carbon cycle. We'll talk about hopefully something that's familiar to you, the greenhouse effect. And then we'll talk about how carbon flows through the system. What's the natural movement of carbon? And you'll learn that there's some cycles that change pretty quickly in terms of carbon, and some that are long-term cycles, over millions of years. And you'll learn that the human interference that has led to climate change is disruption of the cycles. So disruption of the cycles. And more specifically, short-circuiting the long-term cycle, making what usually takes millions of years to cycle, make it so that material is concentrated in the atmosphere rather than cycling through the long term, millions of years cycle. Then we'll talk more specifically about the oceans. The oceans has a very important role in carbon regulation because they're an important source of carbon dioxide to the atmosphere, but they're also an important sink. And that'll give us a clue on some of the ideas that have been proposed to engineer solutions to climate change. Called geoengineering, right? So geoengineering is this idea that we can find solutions at planetary scale. So one of the things that we'd like you to grapple with is how to deal with that. We already know humans have a huge influence on the environment. Your seminar book gives you evidence of that. The engineering articles provide some solutions. So what do you think about them? Is it a good idea, bad idea, ugly idea, all of the above? Okay. And then the last thing we'll talk about phytoplankton as background to the connection to the carbon cycle and connection background to the lab. Great. Okay, so let's start pretty simple with the greenhouse effect. But maybe before I start here, I want to say something about what we covered so far. We talked about climate, and one thing I hope I emphasized is that climate is predictable, right? We know, climate in Pacific Northwest should be a certain conditions of temperature or precipitation in the winter versus summer. So there's some predictability. There's some variation with the variation we call weather, right? So day by day, it's hard to predict what's going to happen, but when we look at 2 or 3 months, year by year, it's kind of the same, right? So think about that. There's some variation that's natural, but there's some predictability of it, right? So what we're trying to figure out is making sure, establish that what we call rapid climate change now is not part of a natural cycle, because we know there is a natural cycle, which variations. But it's important to distinguish that, the natural from the regenerative influence, particularly with that of carbon, associated with carbon. Right? So the hypothesis is that humans are affecting the environment by changing carbon, right? Carbon dioxide in the atmosphere, more specifically. So this illustration, first, you can see on the left panel, especially the natural greenhouse effect. Right? So why don't you tell me, guys? I'm talking all the time. So you've heard about the greenhouse effect. Can somebody articulate that? If you're trying to explain that to somebody, what would you say? How would you explain it? What's the greenhouse effect? Anybody try?
This isn't going to be like a perfect explanation, but I'll try. So the atmosphere sort of functions like a greenhouse. Like you've ever been inside a greenhouse. It traps heat. It's very warm in there, and the atmosphere does that for the sun's energy and solar radiation.
Great. Okay. So a lot of people understand what a greenhouse is, but if you didn't know what a greenhouse is, I mean, you see, you can visualize it, right? So let's try to think about it without using that term, right? It's a good metaphor. I think makes the public understand what that is. But so how does a greenhouse work, right? So, Ben was correct, and that there's no principle. So here's the sun. Solar radiation comes in, and we studied the atmosphere already in one of the chapters. So we see how solar radiation, when it comes from the atmosphere, it starts heating the atmosphere by heating the molecules in it, the different compounds there. And the different compounds react differently to solar radiation. Some absorb it, some reflect it. And subsequently, we'll start understanding that in more detail. But what's happening, those solar radiation that is able to pass through the different layers of the atmosphere. Some are absorbed, like ozone absorbs a lot of ultraviolet light. And that's why certain layers of the atmosphere are really warm, because the ozone has absorbed that ultraviolet radiation. But whatever goes through, basically warms the planet, the solid earth and the water, and that irradiates long wave, a different kind of energy. The energy comes in, and a different kind of energy, and the quality of that energy is reflected back to the atmosphere. And some gases, carbon dioxide, methane, water vapor, are gases that absorb in that wavelength. Whatever comes out, radiating from the Earth, is trapped by those gases. Right? So the analogy with greenhouse is that the glass in the greenhouse allows the radiation to go through. It warms the things inside the greenhouse, but that glass doesn't allow that long wave radiation to escape out of the greenhouse. So essentially, that's what's happening here. It's as I say, it's a natural effect, right? So if you look at geologic history of the planet, carbon dioxide has changed over geologic time. But for thousands and thousands of years, we've had a certain concentration that's been relatively uniform in the atmosphere. So, and that serves to regulate the planet. If we didn't have carbon dioxide in the atmosphere, the planet would be a frozen ball. Right? So it does. We need it. It's nice to have it warm. Right? But what's happening now is that there's more than there used to be, and the signal that human activities have contributed to that are unquestionable. Right? We measure fossil fuels. All economies run on fossil fuels, so we know exactly how much has been burned. And so here's a statistic. It's fairly recent. I could have updated it, but it's from last quarter. So this is the amount of concentration in the atmosphere of carbon dioxide, and 50% of the pre-industrial level. So whatever used to be before, by the actual industry, fossil fuel burning, cement production, change in land use, deforestation, etc. A huge amount, 50% over what it used to be present before this accelerated, sometimes called the Anthropocene. Mark maybe the Anthropocene is this increase in the concentration. Okay? So what has happened is that more of that sort of radiation that used to be trapped, more of it is trapped because there's more of the greenhouse gas. We might have a thicker greenhouse, right? So we essentially get that world, right? So we want to understand this concentration. This is just human. There's such a natural ways in which carbon dioxide get put into the atmosphere and removed. So let's try to understand the cycle to better quantify the human contribution. So let's start with this. This is an interesting data that a lot of you have seen this in some form, but I presented more of the complexity to help you understand more about the oceanography and how Earth processes work. Okay, so what do we have here? We have here over time, all those times are over time from 73 to 89, and the vertical axis is the concentration of carbon dioxide. Most of you have seen something like this, or not just this one, Mauna Loa, Hawaii, the major observatory where carbon dioxide measurements are taken, and there's a long record of it. It's in this observatory all high up in the volcano in Hawaii. And most of you have seen this. If you go to Alaska, the fluctuations the ups and downs are more marked. If you go to the southern hemisphere, South Pole, American Samoa, you don't see those. Anybody know why? I mean, what are these ups and downs up and down there? What does that represent? How come CO2 varies so much? People publish, the CO2 every year is increasing by a certain amount. But we just look at 1 year. Let's look at this beginning year. It goes from like 325 to 335. There's like a 10 parts per thousand jump back and forth. So if you only look at 2 years, you say, I don't know if they're really global increases because look at the huge changes every year. How about Sarah?
Like the ocean stores carbon when it's colder, right?
Um,
So could it be seasonal fluctuations of like the release of carbon into the atmosphere?
That's very good. So what Sarah's saying that one of the possible fluctuations is the role of the oceans. I would say that's a good hypothesis, particularly. But the problem that with that hypothesis in explaining this is that the southern hemisphere has more ocean. So if the ocean was a driver, you would see those more fluctuations in the southern hemisphere. But you're close. How about?
Like the plants in the spring growing?
Great. So how do the plants growing would explain this up and down?
Because like it would explain the decrease because they use the carbon for photosynthesis.
Great. So that is a major driver. So we look at this one, the increase of CO2, this 10-part increase, 3%, it'll be 3% increase per year, is due simply for in the winter when things are decomposing. So if you look at, you go to you look in my yard, there's a lot of decomposing material, right? And then in the spring, there's this big drawdown. Everything's growing like crazy. So all the carbon dioxide of the atmosphere now is in flowers, in grass, and fruits, and it's going crazy, right? So they have these big fluctuations, right? So how come there are more fluctuations in Alaska than in Hawaii? If that's true, we know now that it's a planet.
Well, Alaska has a lot of, like the big, alpine forest, the big forests and a lot more,
Right.
dense plants.
Yeah, there's more vegetation, so the drawdown is greater, right? One reason, and also you could argue that once you're inland, the seasonality is more marked. When you're in the ocean, you live close to the ocean, the fluctuations seasonally are not that great in terms of temperature, right? So the seasonality and the amount of vegetation in the northern hemisphere is mostly, the northern hemisphere more continent relative to ocean than the southern hemisphere. So this big fluctuations are example of that seasonality, this drawdown of CO2 during this growing season, and the decomposition. And if you go to the southern hemisphere, it's more subdued. As our relation is a little bit related to what Sarah mentioned, it's mostly ocean, and the oceans do take in CO2 and remove it, but the oceans, because they don't warm or cool as much as land, there's very little seasonality in the oceans. So there's no like marked growing season and decomposition season in the oceans, because there's not much seasonality. Okay. The remarkable thing, and this is kind of what a little bit less on statistics, is, we compare just 2 years at a row, you do statistics and calculate the averages and compare those two averages, we show that there's no difference. Statistically, there's no difference. Because there's such a huge fluctuation year after year. So the increase per year is tiny compared to the fluctuation within a year. So it'd be hard to tell it apart. But when you look at all those years together, it's clear that there's a trend, right? And in here, when there's no seasonality, it's filtered out, you can see the increase. And the slope, the change, the rise over run is the same worldwide, right? So that clues you that it's not a local phenomena, but it's a global phenomena, because the rate of increase is constant, right? And the rate of increase is consistent with the amount of fossil fuel burn. So here's a way we can separate the natural from the anthropogenic, right? The natural changes are the seasonality, seasonal fluctuations. But if we filter that out, we say, well, maybe we'll get the average, and which is kind of shown by the southern hemisphere where the seasonality is buffered. We see that constant increase. And well, the only explanation for that is, human inputs. Okay, so let's talk about carbon cycle. Okay, so let's take a little introduction to biogeochemistry. This is biogeochemistry, one of the fields that studies global climate change. Bio, living, geo, planet, chemistry. So the chemistry of biology at the planetary scale. That's biogeochemistry, kind of fancy word. Okay? So when biochemists look at the cycling of different elements that are mediated by living things, carbon being one. And they talk about pools and fluxes. Pools are compartments, places where carbon is located. Fluxes are the movements between pools, between locations. So there's four here, right? The atmosphere, the land, the oceans, and the rock. So carbon cycles through them, and in different forms. It's hard to track it, but we're interested in carbon dioxide, right? So we're gonna be focusing on carbon dioxide and see how the carbon and carbon dioxide cycles. So this is a big picture of it. So what should I say about this? Okay, well, the smaller one is the atmosphere, by far. That's the smallest amount of carbon. Your book gives a lot of details of the amounts, where it is, but for our purposes, just think that the biggest reservoir is the atmosphere. The oceans are pretty big. The rock contain a huge amount. Land, both in soils and plants, they're all the same. But for climate, we're concerned about the atmosphere. It's a tiny amount of the amount of carbon that flows, but it's the most active, the most reactive, and the one that affects climate. Right? So we're really interested in this small compartment, because small is so vulnerable, right? It's very easy to disturb it, to make it change. You don't need a lot to make it change. Whereas the other reservoirs are really hard to modify. Okay, so slowly I'm going to show you kind of how we're going to dissect this carbon cycle, Paul's carbon cycle. So this is a big picture. A picture shows cycling. So I'll illustrate. There's two ways in which use carbon cycles. One's the long-term cycle. The long-term cycle is millions of years. It takes millions of years. So let me take you through what happens in this cycle. So let's start with, where should we start? Let's start down here. Okay. So in the rocks here, there's a lot of compounds that have carbon in it in different forms. And it could be carbon that used to be living, or it's carbon that just is in rocks. Okay. So you know about plate tectonics. You know the Earth is kind of dynamic, so the crust of the oceans gets destroyed, and there's a lot of motions on the ocean, on the Earth. And some of the material gets destroyed and gets recycled by volcanism. You look at the plates crashing against each other when they crash active margins. There's volcanoes. So this rock, through plate tectonics, eventually resurfaces and gets eroded. Some of it is some of the carbon is ejected by volcanism. So you get this mountain, some are volcanic, so the volcanism ejects a lot of CO2 in the atmosphere. As this material comes up to the atmosphere, it gets weathered by rain and wind, and that releases carbon as a gas, as CO2 in the atmosphere, or as water as it flows down the rivers. And as this carbon flows down the rivers, the cycle gets repeated. It gets to the ocean, gets deposited, gets buried, deposited to plate tectonics, it surfaces again, it gets weathered or ejected to volcanism. So that's kind of a long-term cycle, millions of years for a rock to go from rock to a gas, liquid, back to a rock. It takes millions of years, right? And then there is the biological cycle, which is actually connected. I'll show you how it's connected to the long-term cycle. So the long-term cycle is easy, right? So rock to rock, essentially. The short-term cycle is seasonal. It's basically respiration and photosynthesis. It's biological. The short-term cycle is biological. So carbon dioxide in the atmosphere gets taken up by photosynthesis, and things are made, and then some of them the majority are eaten, right? So when you get photosynthesis, you get carbon dioxide and water, you get the sugars, and oxygen gets produced, and then heterotrophs use the oxygen, eat the sugars, and eject the CO2 and the water. So in that sense, if it's balanced, then there would be no net gain in CO2 or oxygen, right? Because they produce and destroy, Okay. But it's interesting that happens. A tiny amount of what's produced by photosynthesis escapes decomposition. Let me emphasize that. Okay, so photosynthesis and respiration, if it's balanced, you shouldn't have more CO2 in the atmosphere, right? Or oxygen accumulation, because everything that's used here to produce this would go the reverse when it's consumed, right? But a tiny amount escapes decomposition. How does it escape decomposition? Well, it gets buried. A tree gets eaten by a big brontosaurus. The brontosaurus falls into a quicksand, gets buried, and eventually becomes oil. You guys think there was a company that had that. There's a little brontosaurus and signals that it's fossil fuel, right? But it's kind of miscommunication in the sense that very little of the carbon as petroleum is really from dinosaurs, right? Most of the carbon that becomes fossil fuels is actually in the oceans. We'll talk about phytoplankton. The phytoplankton do this, photosynthesis and respiration. Most of them are eaten, but a tiny amount sink to the deep sea and they get buried. So that organic material that they made doesn't get used and doesn't go back to the atmosphere, CO2, because it's buried. Okay, that makes sense? Okay. So when you bury living things under certain pressure and temperature and time, they become fossil fuels. Right? So a lot of accumulations of oil deposits that people are exploiting now are ancient areas that were highly productive with phytoplankton. Right? Okay. So how does that connect to the long-term cycle? Well, the short-term cycle, photosynthesis and respiration, it enters a long-term cycle by the burial of organic matter over millions of years, and that joins the long-term cycle. Does that make sense? Okay. So what humans have done is taken these fossil fuels this old phytoplankton and dinosaurs, whatever, organic matter, and that would have taken millions of years to recycle. So they take it out of the ground, they put it in your car, and within, I don't know, 0 to 60 in 3 seconds or something, it all goes into the atmosphere. So what it should have taken millions of years to cycle is right now, it's immediately put into the atmosphere. That offsets the balance, the steady state. Okay, so some text to kind of highlight those ideas. I'll show you the picture. There's some text. Okay, so there's a slow cycle that turns scales of millions of years. So carbon cycle from rock to rock, volcanism, weathering, erosion that converts the rock into gases and liquid and flows back to ocean sediments, sinks and form. Right? Formation, I really highlight this as a connection to human activity. Formation of fossil fuels are results of the cycle. Over millions of years, the organic carbon that's buried, that escapes decomposition, becomes fossil fuels. A fast cycle, months to thousands of years, basically photosynthesis and respiration. So photosynthesis captures the CO2, respiration releases it, a little bit gets buried, a tiny amount, 1% a year or less gets buried, escapes decomposition, gets buried, enters a slow million-year cycle, and forms the fossil fuels. Okay. And so I'm going to give you a little quiz, a thought exercise. Okay. So if you understood what I just told you, you should be able to answer this. Okay. This is my car, my dream car. It's a Hummer limousine. Okay. So, okay, why is this statement technically correct? But it's not a good excuse why we should continue to burn fossil fuels. This Hummer limousine, like all fossil fuel vehicles, is really solar powered. Is that right? Okay. So what do you guys think? Why this is technically true? Let's start with the first one. Why is it true that this vehicle is solar powered?
It uses fossil fuels, which comes from organic matter, which was created through some source.
Exactly. Okay. So all living things eventually rely on the sun, right? Okay. So isn't that amazing? I mean, when you put in your car, it's encapsulated solar power. Right? Because the sun is trapped, it's put in chemical energy, and it's put in a form that you can burn. So it's solar power, right? Okay. So why would it's correct to say that it is sustainable?
That's what she said.
No. I'll give you a clue. It depends on the time scale. Right? Over millions of years, it's sustainable, right? Because no matter, I mean, you burn it, but the cycle is going to be completed. It just will take a million years, right? It's sustainable over millions of years. Right?
I don't think that's rational.
Okay. So why I brought this up? It's interesting because a lot of it's about time scales, right? So over short time scales, this doesn't work. I mean, over our lifetimes, or over the life of civilization, right? So I'm giving you the answer. So why is not a... Somebody could say this and say, oh, it's technically correct, and people would agree, right? But why is not an excuse? Well, what's wrong with that rationale of saying, yeah, it's sustainable. Solar power, we want solar power. Yeah, solar power. Sustainable, yeah, sure. And wait, give or take a couple billion years, and we'll be fine. So what's the problem?
For the sustainable part, unfortunately humans don't live, millions of years, so in our lifetime, the fossil fuels that we burn, they're just gonna stay there for, our lifetime, and it's not really
It's sustainable over timescales that are first of all, practical, and they do not address the consequences of burning on the short term. Right? The rapid changes that occur, it doesn't helped us, sustainable over millions of years. But the short circuiting of the system, injecting so much CO2 in the atmosphere has consequences that are immediate, that are more problematic, right? Okay, so this is from your book. I have the other slide of the slides from other books I've used before, so try not to all use all of them from your book, but this is from your book. So this highlights it in the following way. Okay, because all these graphs are complicated because it's a complicated problem. Okay, but this shows you the carbon cycle in a sense as the reservoirs of carbon. So the ocean's huge. This is gigatons of carbon. Giga is 10 to the 9. It's 10 to the 9 kilograms. So a lot of zeros. Okay. But the point here is that everything except the red is the natural cycle. So the oceans, the atmosphere. The atmosphere is a tiny compartment. The ocean is a huge compartment. Living things. Actually, living things is a big compartment. A lot of carbon's in living things. Some's in permafrost, some's in soils. A concern with permafrost, you'll read it in your book, is that this melts. Permafrost has a lot of carbon there's trapped gases and stuff, so there's a lot of methane and stuff can be released. Right? So this is a natural cycle, and this is a tiny amount that escapes decomposition. Right? So there's photosynthesis and respiration, the cycling, and a tiny amount, this tiny 0.2 gigatons per year, is the unbalance. Some of it slowly escapes decomposition, and some of that becomes fossil fuels over millions of years. Right? Hopefully it won't confuse you, but we were to study geology and geochemistry over millions of years. This tiny amount also explains why, over geologic time, over millions of years, actually CO2 has decreased in the atmosphere. It doesn't help as much because the increase now is important, but over millions and millions of years, the CO2 has decreased, basically because of this tiny unbalance. A little bit escapes decomposition every year in the oceans. Okay. But for purposes, let's look at this. Okay, this is the tiny amount naturally that gets removed per year. This is the human inputs per year. And you add this together, we get this. Humans add about 9.2 gigatons per year, and the net removal naturally is like 0.2. So use your calculator. How long would it take to, using the natural sink, to get rid of what humans put in a year? How many? Can somebody just do that? Just divide. Yeah, we have 9.2 gigatons per year put in by humans, and 46 years. It's actually more. Your book gives you more details because we're simplifying here. Carbon just as carbon is CO2, but carbon takes many different forms, and each form cycles differently. So, but let's look at that number, right? So 46 years to get rid of what humans put in a year. 46 times as much, right? And then add the fact that humans have been doing this since the Industrial Revolution. So 200 years. So multiply 200 times 46. Right? So it's a lot of. Naturally, it's going to take, even what's there now, it's going to take thousands of years. Naturally, right? What should we do? Geoengineering. No. Maybe. I don't know. You guys think about it. Okay. Okay, another picture. You don't need to memorize that. Why am I showing you this? It's just to highlight that idea of natural versus anthropogenic cycles at a relative scale. So this is another way. This is from the IPCC report. The International Panel on Climate Change, United Nations, says that all this scientists from all the world get together every so many years, produce this report. And so this is from that report. So it shows you the same things. All these boxes are compartments, the atmosphere, the oceans, et cetera, and then the red is the human input. So again, it's showing you that these huge reservoirs, but what humans are doing is short-circuiting the system. The human input's fairly small compared to the natural cycling, but the key thing is that it's unbalancing the system. Right? You don't need a common argument is like CO2 in the atmosphere is such a tiny amount, and humans are putting 0.3% up a year. So one of the arguments is like, such a tiny amount, why should we worry? But the idea to counter that is, if you imagine a swimming pool, And then let's say, I'm going to put a number, let's say this has 1 million gallons of water in it. And it's in steady state, so there's that intake and outtake. So we want to keep the water level, the in has to equal out, right? So how much would it take to unbalance this to make it overflow? How much? I'm not looking for a certain amount. It's like, what would it take to overflow it? Just anything, right? 1 million, the tiniest amount would unbalance it, right? So that's a counter argument. The argument is like, oh, why worry about this tiny amount? Well, if you're having this huge amount, that's not the point. The point is the balance, right? So there's a balance right now, natural balance, and then what humans are doing is, putting a huge amount in pretty rapidly, right? So that's unbalanced in the system. Great. Okay, so a little more detail of the carbon cycle, because humans have put a bunch of stuff in the atmosphere, but only about half of what humans have burned actually ends up in the atmosphere. Where does the rest go? Well, here it tells you, right? So again, very important. Not everything that humans have put in burn has ended up in the atmosphere. Why? Because the oceans take up a lot. So in a sense, I'm telling you all the natural sinks. So the natural sinks are offsetting some of the human inputs, but not a lot, right? Not enough. But it's important to know because that's what we're moving to is understand the role of the oceans. Okay? So about half stays in the atmosphere, 43%. Where does the rest go? Importantly, a lot of it's absorbed by the oceans. So half of the atmosphere, half of what remains is in the oceans, the other half is in land. Okay. The part that's in land is interesting. There's been a lot of research, and it seems that it's actually an outcome of, there's been a lot of deforestation, and there's been a lot of replanting. So good news, those young plants being replanted are sucking up a lot of CO2. The bad news is that it's just temporary, right? It's like as they grow, they're going to slow down. The rate of uptake is going to decrease, and then they're going to be logged again. So let's focus on the ocean, right? So the ocean, a lot of it goes into the ocean. Okay. Ocean absorption. So we're going to study ocean absorption, right? So the role of the oceans in the carbon cycle, and that's going to lead us to a little explanation of geoengineering, which is what you're going to read about and discuss in seminar. Okay, but I think it's time for a break. So let's come back at quarter after. We'll come back at 7. Stretch, go to back. Okay, let's take this time. Let's restart. Okay, so where did I left off? So far, okay, we talked about the carbon cycle. You know what the pools are, and the fluxes between those pools, and give you an idea how what's the natural cycle of carbon, can simplify it, but recognize it's a short cycle, it's mostly biologically driven, photosynthesis and respiration. There's a long-term cycle from rocks to rocks, and they're kind of connected to the formation of fossil fuels, right? The fossil fuels are a formation over the long-term cycle, but it's generated by the short-term photosynthesis respiration process and the little amount that escapes decomposition. And most of that escape from decomposition occurs in the oceans. And that's evidenced by the fact that human activities have increased the amount of CO2 in the atmosphere, but only part of it is accumulating, because some of it is being used up by growth of new forests and the oceans. So here we go. Let's talk about the oceans. Here are some clues about the carbon cycle. Okay. Your book talks about this biological pump. There's two ways in which carbon gets transported to the deep sea. I like this figure better. So, anyways, you'll have it in the slide, right? Okay, so this is the way in which the oceans can be both a source and a sink of carbon. They're a net sink, but it's important to recognize that they do both. The oceans can be a source of carbon to the atmosphere and a sink. Overall, they are a net sink. Overall, the result is that they're So there's two ways in which we can get carbon moving from the atmosphere down into the sea. And we need to understand that the sea is stratified, right? Remember now we talked about stratification, that was our very first lab. So this illustration shows you a stratified ocean, surface ocean, and a deep ocean. So stratification. It's almost like our experiment, right? The salty water from the tank is down here, and then the surface water, a little bit bluish up here. Okay. So why should we separate the surface from the deep ocean? It's a real separation. And if you remember from our lab, there's also implications if there's stratification, that the exchange between gases and particles is restricted between the two layers. So the surface ocean is in contact with the atmosphere. So CO2 goes in readily, CO2 goes out just by simple diffusion in and out, just chemical diffusion in and out. Okay? So how do we get this CO2 that's cycling between the air and the surface of the ocean to the deep ocean? So let's talk about this right-hand little panel. We'll call this the solubility pump. The solubility pump is simply the process by which carbon dioxide mixes with ocean water, and when that water sinks or upwells, you know when those two things happen, right? Sinking when you get formation of deep sea water by increasing density, things get denser and colder and saltier, they sink, or there's upwelling through winds, and whenever there's downwelling, you can get CO2 into the deep sea. And when you have upwelling, you get CO2 from the deep sea up to the surface. Okay? So why is that important for our purposes? Is that if we can get carbon dioxide to the deep sea, we can sequester it, we can keep it away from oceans, from surface circulation, from the atmosphere, for the time it takes for the deep ocean to circulate, which is about 1,000 years. So we get this molecule that's up here, this molecule is going up and down, right? It's put up in the atmosphere, it gets put into the water, we can get it to the deep sea, then it's caught in there for 1,000 years. And if for some reason it gets deposited into sediments and buried, then it becomes part of the long-term cycle for millions of years. Right? Okay. So one way to do this movement is simply physics and chemistry. Solubility pump. The other one's more interesting, the biological pump. So what's the biological pump? Okay, the biological pump is CO2 is taken up by photosynthesis, makes little algae, phytoplankton, that gets eaten. Whatever eats it gets eaten, ends up with fish. So there's a cycling up here. It's a food web. So CO2 forms the base of the food chain, things get eaten, they respire, they get decomposed, and CO2 goes up to the surface. A tiny amount of composition. How does it do that? By sinking. It sinks faster than it gets eaten. So if it sinks faster than it's eaten, it ends up in the deep sea. And if it gets in the deep sea, again, it circulates over thousands of years. Or if it gets in sediment, over millions of years. Everybody sign? Okay, great. So there we go. The biological pump and the solubility. Okay. And your book describes them in other pictures. I like this picture better. Okay. Here's an example of the amount of carbon dioxide in the oceans if it's a source or a sink. So it's not even. Right? Another lesson in the complexity of our studies is that there's a lot of variation. Variation in how sea level rise affects the world. So this variation in how oceans take in or put out CO2. So the red is more CO2 out, the blue more CO2 in. So let's see what the pattern is here. Okay. So, look at that. Along the equator is where most of the CO2 output is from the oceans. Right? And most of the CO2 where it's removed is in high latitudes. Look at this. North Atlantic, around Antarctica and high polar regions. Why? You guys should know this one. Why? Why do you think this is? And this is just, I'll give you a clue. This is because of the solubility pump. So what would explain this pattern. Let's start with the equator. How come the equator is a place where CO2 goes out from the deep sea to the surface? What's happening to the equator? And I'll give you another clue because we looked at it last week. This is the coast of Peru and Ecuador. A lot of it's being put out there. Also, coast of Northern California, and along the equator.
It has to be something with the sun and heat, right? No?
No.
No, okay.
I mean, I guess
Fair
it's
enough.
really kind of related. The sun and heat affect what the process is.
Upload.
Upwelling. What you guys say?
Oh,
Same thing. Upwelling. Great. Okay. So we talked about upwelling here, right? So this is the coast of Peru. So what's the Peru? Here's the equator. The world equator. Here's okay. So if the wind is blowing, the wind. Okay. So remember, there's the water goes to the left, and you get upwelling, right? Hey, what's happening here in the equator? How come there's so much upwelling in the equator? There's no coastline. Okay, so I'll give you a clue. See, the wind goes in here, and then in the equator, the winds are blowing from east to west. Here's the equator, right? So the wind is blowing east to west. Okay, there's no continent, right? So the water in the northern hemisphere, as the water pushes it, where is it going to go? Because of the Coriolis effect. To the right or to the left? Huh?
To the west.
No. The wind is blowing from the east to the west, right? So in the northern hemisphere, if the water is being pushed from the east to the west, this is deflected to the right of the motion, which is towards where?
To the north.
To the north. Right? Does that make sense? Does it make sense?
Yeah, it doesn't.
Yeah, you're in the northern hemisphere, so the northern hemisphere, I'm the wind, and I'm pushing this chair, right? But the Coriolis effect's making it drift to the right. So as I push it, it's like, I deflected to the right. So the wind is pushing it, and then it gets deflected to the right. What happens in the southern hemisphere? The wind is pushing it, and it's deflected to where? To the south. So if the water's spreading north and south, what happens? You get up.
Oh, you get upwelling.
Upwelling. Okay. Yay. Okay. Isn't that cool? So all this upwelling region, it's a very interesting upwelling because you don't need a coast. Isn't that weird? Northern hemisphere, the water's pushed to the right, left. You have welling in the equator. Okay. And that explains why actually the equatorial waters actually have very low nutrients. Unless,
What's happening, sorry, I don't know like geology, but
Geog-
the other
geography.
geography, what's the other red spot?
This is kind of Gulf of Alaska. There must be some upwell in there too. Yeah, that's what. Yeah, it's the only reason it's coming from the bottom, right? Whereas, you remember when we talked about the deep sea circulation, most of the deep ocean water gets formed in North Atlantic off of Greenland. Water gets really cold, southeast sinks, and it drives the ocean circulation. Okay. Quick thing about, maybe I'll talk about it tomorrow. I was talking about ocean acidification. There's a little bit of chemistry. Takes a few minutes, so I'll just mention it. The problem now with more CO2 in the atmosphere is called second CO2 problem. It's the climate, but more CO2 in the water makes the water a little bit acidic, and marine waters tend to be what's called buffer. The pH doesn't change much. They change a little bit, it has a big consequence. It has some consequences to marine life, but I think it's good to this. We'll discuss that in a different lecture. Distribution of chlorophyll. So how is the collection of phytoplankton, right? So phytoplankton are taking up CO2, and as you can So, and then the green is regular amount. So you can see areas of high productivity. The upwelling zones are areas of high productivity. There's some upwelling here too, in Antarctica. Okay, so phytoplankton are very important because they take up a lot of CO2 and some of them tend to sink. Copolithophores are these tiny organisms. They're basically invisible to the naked eye, even with microscopes, they're fancy microscopes. They're about 5 micrometers, a millionth of a meter is a micrometer. So they're teeny tiny. But they find these accumulations. So these clouds are really accumulations of billions and billions of these copolithophores. And the copolithophores make their little shells out of calcium carbonate. And carbonate has carbon. So they as they grow, they take a lot of carbon to build their soft tissues, their hard tissues as well. And then when they sink, they remove a lot of CO2. Okay? So it's a part of the natural cycle. Okay? So little connection to seminar. Seminar, you were reading about the influence of humans on the environment and mostly the negative aspect of it. But I think to consider is this idea of we understand how the system works. So can we use that knowledge to come up with a solution? So here's a solution. I'm just going to present a solution. I think your task is to think about, in a broader context, right, in social science, natural science. So what do you think of the solution? Okay, so can we remove CO2, this is a box, can we remove CO2 by fertilizing the oceans? We know that there is this biological pump, and the biological pump accounts for the removal of carbon already by having some of the prime production, escape composition, and then in the deep sea. So if we fertilize the oceans, we can accelerate that pump. The article that I gave you to read, I don't think it's lengthy. It's kind of technical. It goes over all the different things that we propose. So I don't expect you to, know the technicalities, but know enough to get a sense of what are they based on in terms of our knowledge of how climate works. But very important for you to wrestle with the idea of if it's a reasonable solution or not. Okay, so here are a bunch of different things, and I won't go through all of them. You can see them. They're being mentioned under White Sky, and they're mentioned in the article, and you'll see them again and again in the news, maybe. Right? So there's basically 2 categories of geoengineering solutions. One is to deal with radiation balance. So we know a big influence of climate is the sun. So one is put a big reflector, put a big mirror in the sky, like put your finger on the sun, send millions and millions of mirrors out there. On their white skies, basically this aerosols in the atmosphere, whiten the clouds, more reflectivity. Right? And the second category of geoengineering is to remove carbon management. Okay? So here's pumping CO2 into the rocks, pumping into the deep sea. Hey, look at this one, iron fertilization of the sea. So let's look at this one in more detail. Okay, so this kind of summarizes the biological pump, right? So biological pumps, a lot of detail here, but it looks pretty, right? There's all this CO2 being taken up by living things, fuels the food chain, and a tiny amount escapes decomposition, ends up in the deep sea, sort of circulates for thousands of years in the deep sea, trapped in the deep sea, before it comes up through upwelling, or becomes ocean sediments, millions of years, becomes fossil fuels, millions of years to cycle. Not all of it becomes fossil fuels, but some of it could be. Okay, so the idea of ocean fertilization is, we'll make this box bigger. Maybe only like 1% escapes decomposition. But if we increase this box, that will increase the natural spigot to remove the CO2, right? So how we do it? I mean, it's very expensive to fertilize the oceans, but there's a discovery, and it wasn't associated with the ocean engineering at all. It's just as a scientist, and I remember when I was in grad school, was all these discussions about it, is just to understand what controls the productivity of the oceans. And it was found that in some areas of the ocean, the limiting factor, what limits how fast plants are going to grow, is the amount of iron. Like we need iron too. If you don't get iron, you get anemia, right? So the plants in the ocean that live in the open ocean, in certain areas that are far from the continent, because iron is very abundant. It's one of the most common elements. It comes from erosion from land. But there's some areas like Antarctica that cover by ice. There's no continent exposed. So there's a little iron. So somebody found that just a tiny amount of iron is sufficient to create these huge blooms. And in fact, there's been all these experiments. They've gone to different parts of the world and then put soluble, basically add vitamins to the water. And it's shown that it does increase tremendously the productivity. If you're interested, I mean, you'll read that article, or if you're interested, I don't know, most of you chosen that project already, right? But this is an interesting project, because people jump the gun, there's no world body that said you can't do this experiment. Some have done by scientists, some have done by rogue. People just say, oh, we're going to do it. And then, in fact, it was so popular, there were websites that would sell you credits, ocean credits. Give us, $1,000 and we'll fertilize this patch of the ocean for you. And you'll be removing some CO2. So there's been a lot of things like that that have been actually occurring. So, good idea, bad idea. So that's what we're going to discuss, hopefully, seminar. Okay, so I'm going to switch gears. We're going to talk about phytoplankton, because it's related, right? Phytoplankton. And we're going to have a chance to see it in the microscope. So I'm going to do a kind of quick, just to give you some illustrations of it, highlight a couple things, and then in the lab we had a great time, right? The only potential problem, I hope it is a problem, is that it's winter time, so there's actually not that much out there. So I'll go on Wednesday or maybe Thursday morning, and I'll just get a tow for a long time. Tow a lot of water. If not, we'll watch the King Toads videos. We'll watch some Jack's Gustav reruns. I don't know. I'm sure we'll find something to look at. Okay. So why phytoplankton? Okay, well, the base of the marine food chains are extremely important for the process I just described, right? Most of the ocean seeing the biological pump is all due to phytoplankton. These microscopic organisms, and the ocean, some of them have calcium carbonate, which it's more carbon being taken out. So it contributes tremendously to the carbon cycle. Locally, you've been learning about the importance of coastal systems. Coastal systems, a lot of productivity is from phytoplankton. And as you learn in subsequent lectures, the coastal system is disproportionately an important place where carbon sequestration occurs, removal of carbon naturally. So we need to protect it, either to keep that sink, or be a believer of manipulation to increase that sink. Right? But they're definitely losing a lot of productivity in the coastal system, which is a huge area where the natural sink of carbon occurs. Okay? And I put a bunch of other reports for phytoplankton, right? Based on the marine food chain, half of the oxygen produced is from phytoplankton photosynthesis, and they sequester carbon, right? So some of it escapes composition in the coastal zone, the deep sea. Maybe this is good. This is a general biodiversity in the oceans. Yeah, I'll talk about this one. Okay. So you probably saw this in your general biology. The life is organized this way. There's prokaryotes, which are unicellular organisms with no distinct organelles. Eukaryotes can be unicellular, multicellular, and they have organelles, like nucleus, chloroplast. Right? That's the main distinction between those groups. Bacteria there's two groups, the bacteria and the archaea. And the size indicates they're huge. You don't see them, it's microscopic, but they're very great biomass in the plant. To introduce the phytoplankton, maybe I'll mention this bottom, the protista and then the plants. And on land, most of the photosynthesis is by plants. Plants are a more complicated group. They have a vascular system, some are flowering, et cetera. In the oceans, the majority of photosynthetic activity is microscopic, and it's part of the protista. The protista doesn't have a nice little circle around it because the protista are kind of bizarre in the sense that they have characteristics of animals, fungi, and plants. So in the microscope, we're going to look at basically a protista, some of the algae are protista. And some of the things that you see are heterotrophic, photosynthetic at the same time. They're photosynthetic, but also eat other things. So pretty interesting. Okay? So maybe that's a main distinction that I'll point out in this video. They're very small. So here's the relative sizes. We're going to be looking at things that are going to be around here, 20 to 200 micrometers. A micrometer is a millionth of a meter, and in the lab I'll give you I have an informative thing of metric prefixes. In science, you should use a metric system. So all these prefixes is micro, milli, centi, kilo. Those are metric prefixes. So I'll give you a table of that. Most of the things we're going to see, mainly because we can see on our microscope, are going to be this range, 20 to 200 micrometers. Anything smaller is hard to see unless you use the fancy scopes that we'll give you a tour on. It's like scanning like the microscope can go beyond. So what's really tiny? Femtoplankton, this is also viruses. Picoplankton are bacteria. Nano, micro, that we were starting to get the photosynthetic ones. So the major one is in mycoplankton. That's what we're going to look at this Thursday. Oh, here's a good distinction. Okay, so it's easy to use these two terms interchangeably, but I guess part of your education science is to be more specific about what you mean when you talk about photosynthetic organisms. So there's algae and plant. They're used interchangeably for good reason. They're both photosynthetic, but in taxonomically they're different. And it's important to make a distinction now because we're talking about phytoplankton and most marine productivity algae. So algae primitive, mainly protozoas, some multicellular ones, but very simple in terms of their organization. So like kelps or algae, they're huge algae, but they still pretty simple compared to plants. So plants that dominate land, multicellular, eukaryotic, and have special tissues, like even think of a tree or rose bush or something, right? So let's start making that distinction. So most of the things we're going to talk about is going to be the algae. We'll talk about the marine world. And then before I go, I'll make another definition here. I've been using this term kind of liberally, but it's important to know it's the primary production. Primary production. Okay, primary production. So let's look at the word each word. Primary means the first, so that you can think of as the base of the food chain. Production of what? Production of organic matter. So the first stage in the production of organic matter. So typically that's due to photosynthesis. Right? So photo means light, and making with light. Right? So most organic matter, most of the primary production is photosynthesis, but are they the same? No. Why? Anybody know why? We can't use them interchangeably. Sometimes you could argue you could, but technically you shouldn't. Why? Why is photosynthesis not the same as primary production? Or that's a distinction between? Yeah. Yeah.
Other things can be used as the base.
Exactly. Other things can do this, can make organic matter from carbon dioxide, which is inorganic. So the first movement in primary production is convert that to organic carbon, organic carbon. Photosynthesis does that, but there's something called chemosynthesis. So in the deep sea, in tide marshes, you have chemosynthesis, so bacteria do that. So there's other organisms that can make organic matter without light. So technically speaking, we shouldn't equate them. In the surface of the ocean, most of the productivity is through photosynthesis. That's why people often use it interchangeably, but you should know that it's not. They're different. Or you can argue photosynthesis is a form of primary production. chemosynthesis in other form. Okay, so some major groups that we're gonna see. We're gonna see mainly the Chrysophyta or the diatoms and the Pyrophyta, Dinophyta. So focus on those two. You can write the other names because if you were looking at the open ocean, you would probably study them. But Chrysophyta is a major group. Diatoms is more the common name, and distinguished from the other ones because they have a shell made of silica. Silica and oxygen. So it's basically glass. They're actually made of glass. Glass is that. Silica and oxides makes glass. So the Chrysophyta are the diatoms. We'll see them, and hopefully we'll see some kind of flagellates, which are motile. I mentioned those other ones because they're important in the open ocean. Coccolithophores are the ones that have a calcium carbonate shield. Oh, cyanophyta, cyanobacteria. So we talked about cyanobacteria today. So in the open ocean, cyanobacteria are actually very important, and they're a relatively recent discovery because they're so tiny. They're for a long time they're undetected. Right? But we're going to focus on these two groups: diatoms and dinoflagellates. Dinoflagellates, motile, have cellulose plates. Sometimes they're naked. Diatoms have silica. Some pictures. Just turn your eye. Hopefully we'll see examples of them in the field and the lab. Diatoms above the line, and flagellates below. Diatoms, because they're very they have silica minerals, a mineral structure outside of them. They're very geometric in shape. So there's circles or triangles or rectangles, little spines. They can be colonial, stick together, solitary. Dinoflagellates tend to be solitary, more organic shape because their plates are made of cellulose, or they can be naked, no plates. They have flagella, so they swim, and they twirl as they swim. Noctilucas means a night light, so this genus bioluminescens. So you see bioluminescence in the northwest, typically this one. And then there's some that are toxic. So I'll show you a bunch of pictures, so I'll talk about some of the interesting things that they do, and then I think we're ready for lunch. This is with the light microscopes, or you're going to see this in the light microscopes. This is very common. It's a diatom. You can almost see as you focus in and out, it has this little grids. So it forms this frustule. This frustule is a skeleton, forms little geometric shapes as they mineralize the skeleton. This is Noctiluca, the one that's bioluminescent. We have a scanning electron microscope, which you will hopefully will see. They just fixed it. So these are pictures that I took from phytoplankton here in the sound with the scanning electron microscope. Some more pictures of the electron microscope. I'm just gonna go through here. Eutrophication, we'll talk about that in the lab. Okay, some more scanning electron microscope pictures. These are bacteria covering this diatom. And it's interesting, the light ones don't have it, so this must have been decomposing. This is a dinoflagellate. This one's Suranitia. This is actually one that causes amnesic shellfish poisoning. So people are really concerned about this one. There's been instances occurring in the Pacific Northwest. So they accumulate in shellfish, and then be toxic. Diatom, chloride diatom. Oh, yeah. So diatoms are interesting. You know, this is a cross section of one. So they have a frustral silica glass, and inside is a cell. So sometimes you focus in and out, you can see the crystalline outer coating or the internal structures. Some pictures. Here's a picture of the Coccolithophores off the coast of United Kingdom. Huge blooms. Dinoflagellates. So dinoflagellates are pretty cool. My favorite, because I did my master's thesis on them. So look like little battle helmets or something. They're pretty cool. And because they're motile, here's a close-up of some of them with their shells, their little plates. And in this case, they're made of cellulose. This is what you see in the microscope. In the Pacific Northwest, we're really concerned with, actually all of these ones have some kind of toxic. This one, when it decomposes, it forms these big foams, and massive bird mortalities have been due to the foams kind of washing off the waterproofing of the birds. So there's some bird mortality associated with that. This one forms diuretic shellfish poisoning, and in Europe it's a big problem. So Europeans that buy shellfish from the Pacific Northwest want people here to monitor for it. So I'm part of that study. We monitor the presence of this Dinophyces. It doesn't seem to be a problem here, but potentially it's a problem because we know that it's potentially toxic. Luminescence, they're bioluminesce. Dinophytes bioluminesce. They're also part of the symbiosis. We talked today about symbiosis. They're making all these connections. So in coral reefs, the algae that live within the tissues of corals is actually dinoflagellates. From red tides, this is probably Noctiluca here in the Pacific Northwest. Red tides and bioluminescent ones. I think that's it. I think I'm gonna stop right here. Oh yeah, last one is, so all these ones are toxic. You can't get them. You can't get poisoned by swimming in the water, but most of them accumulate through shellfish. So they can paralyze you, make you forget, have diarrhea. So a lot of things can be harmful. So there's a lot of research on them here because shellfish industry is so important. The Pacific Northwest. Okay, so I'm done. Take a lunch break. We'll see you here at 1 for the afternoon session.